Let's look at one of the strangest atoms in physics, positronium. It doesn't have a proton at its core. Instead, it's built entirely out of a matter electron bound to an antimatter positron. Because matter and antimatter violently destroy each other on contact, this purely leptonic system is highly unstable. It exists for just a fraction of a microsecond before self-annihilating in a flash of gamma rays. It's also electrically neutral, which makes it incredibly difficult to manipulate. When positronium moves through space, its behavior creates a conflict. We see an electron and a positron, but we have to determine if they act like two separate particles tethered together or project as a single, unified entity. Resolving that tension forces us to define exactly what constitutes a single object in quantum mechanics. In 1925, physicist Louis de Broglie hypothesized that all matter possesses a wave-like nature. We have successfully proven that wave nature for standard matter, from single electrons all the way up to large molecules, but composite matter-antimatter systems remained a total unknown, simply because they destroy themselves so quickly. This image shows a standard diffraction pattern. When you shoot a wave through a grating, it produces these distinct symmetrical bright spots, which act as a measurable signature of wave-like interference. If we managed to fire a beam of positronium through a similar grating, the geometry of those spots would give us our answer. Two independent particles would cast two overlapping wave patterns. A unified atom would cast just one. Capturing that pattern requires reading a coherent quantum state from a carrier that is destined to destroy itself. To pull this off, researchers generated a highly controlled, tunable beam of positronium atoms. They fired this beam straight through a 2 to 3 layer sheet of hexagonal graphene. The graphene sheet doesn't create the wave character of the atoms. Instead, its lattice structure acts as what researchers call a projection conditioning map, a specialized physical filter with the exact right spacing to expose the underlying wave structure that already exists. Getting a clear reading is difficult because of a phenomenon known as the Born elastic amplitude. Since the electron and positron share the exact same mass but hold opposite charges, their coherent signal essentially cancels out, making the resulting wave output extremely weak. To isolate that faint signal from the noise of the atom's own destruction, the team used precise time-of-flight selection. By timing exactly when events hit the detector, they could filter out the chaotic gamma-ray background and isolate the specific surviving positronium atoms that made it through the graphene intact. Building this intricate filtering system was a strict prerequisite. Without it, the unified quantum readout would remain completely hidden in the noise. This animated graph shows a core principle of the de Broglie relation. A wave's physical length, and therefore exactly where its diffraction peak lands on a detector, is determined by its total momentum. If the electron and positron behaved as independent parts, they would each have a lower individual momentum. That lower momentum would cast a wider diffraction pattern, creating a peak far out on the detector at exactly 16.2 millimeters. But when the detector recorded the hits, that 16.2 millimeter independent peak was completely absent. Instead, a single prominent signal appeared at exactly 8.1 millimeters. That location perfectly matches the required geometry for the total combined momentum of the bound system. The spatial geometry of that peak provides the proof. The positronium rejects behaving as two separate pieces, and instead projects a totally unified bound state. This experimental data anchors a much broader theoretical perspective, known as the TCGS-SEQUENTION framework. Under this framework, the result is an example of carrier-independent invariant persistence. This suggests that observable reality is not defined by piecing together local, three-dimensional physical parts. The physical mass of the electron and positron, and the fact that they annihilate, makes them a temporary, contingent carrier. The true permanent structure that the graphene exposes is the coherent, bound relationship between them. Even when you swap out a stable, familiar quantum particle for an exotic, neutral matter-antimatter system that destroys itself in microseconds, the persistent relational structure remains unified and readable. Because this bound state acts as a single coherent wave that happens to be electrically neutral, it holds a massive operational advantage for future laboratory work. Standard particle beams are heavily influenced by the environment around them, But as a unified, neutral entity, positronium can travel in a perfectly straight trajectory without being deflected by stray electric or magnetic fields. This specific combination of traits makes positronium an incredibly precise tool. It opens up new methods for next-generation quantum surface sensing and highly sensitive gravity measurements involving antimatter. The fact that this pattern survives even while its physical components vanish suggests that the identity of an object is defined more by its persistent relationships than by its fleeting constituents. In this experiment, the relationship itself proved to be the most stable thing